All right. Yes, I did. So there are a few. Oh, good. All right. So you actually have a few. Travis, be nice. You have a few forms of the equation of a line, and I know you're the first one you're going to say is what's your most famous equation of a line that you're thinking of, Rafaela? Yeah. Y equals mx plus b. If we wanted to use function notation, we could certainly say f of x equals mx plus b. And can you remind us m and b? Okay. So that's the slope, and this is the y-intercept. And we like that form. It's calculator friendly. Like if you solve for that form, you can go right into your calculator and plug it in, right? And it's also the first one we taught you, I think. And if you look at a graph, if you can actually see the intercept and you can estimate the slope, it's a nice one to estimate. There are two more. One which I think is incredibly useful and one which is just sort of the standard. Elizabeth? Did I already tell you that? No, you remembered it? From Algebra 2? Who was your Algebra 1 teacher?
And then before that,
you need to thank them. That's awesome. All right, so.
I'll find her. I'll hunt her down. I feel like stop it. She really is. Did you yell at that Brad?
No, I didn't. All right. Maybe. Can you give me? Do you remember it, Elizabeth?
Yeah.
Y minus y1. All right, Travis, turn around up here. And just so you understand that that we didn't make this formula up. If you actually divide both sides by x minus x1, you get m equals y minus y1 over x minus x1. And doesn't that sort of look like the equation for slope? Okay, so we just rearranged that. And the important thing to remember here is that let's see. This y, and this x, they stay y and x. Let's see if I can erase. Nope. All right. I thought maybe I could erase just the black. I was not. And so in this case, m is the slope. You have to find out what that is. And then x1 and y1, that's a coordinate. All right. So if I give you a point and give you a slope, all you need to do is plug into that equation. And that equation is just as right as the slope-intercept equation. Now, unfortunately, it's not as calculator-friendly, but it's not a big deal to make it calculator-friendly. Just a little bit of algebra. As a matter of fact, you could even just do this. Y equals m times x minus x1 plus y1. Just add y1 to both sides. Now, y1's not the y-intercept, but if you distributed and then combined like terms, you could get it to look like slope-intercept. All right. And then standard form is ax plus by plus c equals 0. So something x plus something y plus something is equal to 0. And you could convert this to slope-intercept form if you solved for y. Okay. This doesn't have the slope isn't looking at you. As a matter of fact, if we had to solve this, just check me to make sure I'm right. I get negative ax minus c. So far, so good. Then divide everything through by b. You'd get negative a over b x minus c over b. I divided b by both sides. Is that okay? So look, the slope here is negative a over b, and the intercept is negative c over b. So you understand that this little b is very different from that big B? Okay. All right. Great. Standard form. And I think the book actually has a blue box that says, like, these are the three formulas and these are what they're called. All right. So in that respect, I know you keep up with the reading every night, and you probably pay particular attention to the blue boxes, right? The blue boxes are what, like, after they go through their long explanation, hey, this is a summary of what we just said. And when we're, trying to get through a lot of homework, that looks well. Do you see? I'm getting there. See?
Oh, yeah, no, I
Yeah,
don't know.
yeah. Oh, all right. See, I never believed that. I believe you, but I always, like, students always say, like, oh, I'm wondering what I had next. And I'm like, no, you didn't. You just want to know how many minutes we have left. But all right, fair enough. All right, so let's take a look. Yeah, I'm getting there. Well, that's, see? Oh, yeah. All right. But see, look. So it's Thursday. Oh, I see. It's not all that clear. Yeah. All right. So let's take a look at number 8. Let's see. Miles, would you read number 8 for us, please?
Sure.
Thanks.
A car that costs $19,200 in 1998 is depreciating at a rate of $2,500 per year. Write a formula for the value V of the car T years from 1998. Use T equals 0 in 1998. Remember that depreciating means decreasing in value.
All right, so we want to come up with a formula or a model that would show that every year the car decreases in value by the same amount. All right. All right, so take like 15 seconds. Think it through. Try writing something down. Great.
Oh, what is it? I don't remember. It's that thing on your calculator.
Oh, is it something R to the T?
Oh, okay. P naught. We will use P naught but I want to be clear. When we talk about depreciation, there are two kinds of depreciation, and in this case, we're depreciating at a constant amount per year. And what you were doing last year, I think, when you did depreciation, you were doing a percent every year. Like, it decreased 10% every year. And there's a big difference between that equation, which was, what kind of equation was that?
Population.
Yeah, it's like compound.
Yeah, no, it's not compound equation. It was a very specific type of function. What kind of function was that used? That's right. It was exponential. That's great. I'm so glad you said that. Awesome. Euler. I don't know if Euler had anything to do with it. With E? Yeah, okay. So when we talk about exponential depreciation, that uses like P naught A to the T or something like that. This, we're not talking about it decreasing a percentage every year. We're saying it decreases the same amount every year. So when something decreases the same amount, the same constant amount every year, you actually should be thinking in your mind, that's a linear depreciation. It's going to go down the same amount every year. And if it helps, you can actually do a little table. Like, okay, what's it going to start off in year 1? Is it year 0, then year 1, then year 2? And see if making that little table will help you. If I had to jot down a table, I'd be like, all right, 1998 is year 0, and it's 19,200. In year 1, it's going to go down 2,500, so that's 18,950. Nope, I did that wrong, didn't I? 18,700. Is that better? Second year, it's going to go down. No, okay, thanks. I'm having problems subtracting. 17,700. It's going to go down another 2,500. All right. I'm not quite sure exactly what's going on, Evan. But I know, but it's distracting to me. Another 2,500, so that's 15,200. So if it helps, make that little table and think, all right, what's going on here? All right, Monty, thought or idea?
B equals 19,200 minus 2,500 T.
All right. I left a little space there, right? All right, so V of t, so the value is a function of time. Time is the input. And I took the 19,200 and put it on the end. And then Monty's saying minus 2,500 t. So when t is 1, we're going to subtract 2,500. When t is 2, we're going to subtract 5,000. We're going to subtract 2 years' worth of that money, right? Do you want to... Do you want to ask a question? Like, you gave a very quick answer, and that was awesome. Do people want to ask a question on how Monty got it, or it makes sense when someone did it, right? How can you give me like a quick insight? Like, how did you actually do it? Like, what were you thinking?
I knew that the value had to equal V, so V had to equal everything else. I started off with 19,000. That was the initial cost.
Okay, that was an important sentence. Hold on, wait for that. Monty said he started off with 19,200 because that was the initial cost. All right, so this is the initial cost, and in this case, what is it? Like, if this is a linear equation, what is that initial cost in terms of a graph or in terms of mathematics, Michelle? It's the y-intercept or the b value, right? And that, do you see that's why I put it on at the end? All right. And how about that? Oh, this is the slope or the m value. What are the units of this slope? Dollars per year. The slope is a rate of change, right? And look, $2,500 per year. So dollars per year. Whoops. You all just did a whole lot of really, really good talking. Do you have any questions? Because I mean, we're going to do some more, but that was great. How some of you pieced that all together, found your clues, and put it together. You good? Yeah. Yes.
You can't just do T equals. I mean, like, you can't just do, like, final cost equals.
No, because it's not asking for what the final cost is. It says write a formula for the value of T, a value of V, T years from that date. Okay? Should we try another one?
Yeah, sure.
Tom, you all right?
I just everyone happy was like, can we switch it? Like you can write it
Oh yeah, you can totally write. You can write it the way Monty said it. 19,200 minus 2,500 T. I specifically did it though. Do you understand as a teacher why I did it that way? Right? I wanted to help you see it. Okay. Corinne, we good? Sam, we good? Mo? Miles? Travis? All right, good. We have representatives from every column that are good. All right.
Wait, we didn't have a
I said Sam, right? All right. Let's take a look at D. All right, another kind of word problem. This time it's given to us in a table, and I think we give you fewer problems than we should in tables. All right. Andrea, read for us, please.
The following table shows the cost for organizations such as different number of special design features.
All right, and we have this table, and the first thing we want to do is, I don't know if it's show, but let's talk, let's discuss why the cost appears to be a linear function. Are there clues in that table that might indicate that? Elizabeth, what might be indicating to you that it looks like a linear function?
As the number of shirts increase, the cost also increases.
All right, so definitely the number of shirts increase, the costs increase. I would agree with that. Now, just because one increases and the other increases, does it mean it has to be linear? Not really. What's going to be the key for whether it's linear or not as we look at a table of data? Peter?
Slope, like whatever never mind.
You sure?
Yeah.
You were looking right.
I think he was too.
Yeah, I think he's trying to say like if the rate of increase.
All right, so Corinne?
Like the ratio of shirts to dollars.
Yeah. So this rate or ratio, if that ratio is constant, the rate of change, if the ratio of changes. So let's have, all right, we should pick 2 points and then compare it to another couple points. So let's pick these 2 points. If we want to do dollars per shirt, how did the dollars increase? How many dollars did we increase? 360 minus 165? 195. And how many did the shirts increase? 50 minus 20. Do you see how that looks like a slope? Okay, so 30. What'd you get? I can't do that in my head, but it's like what? 6 point something. What is it? 2.5? 6.5. What is that number if I had to say, what's the real world, what are the units on that, and what's it mean? Evan?
$6.5.
Yep, $6.50 a shirt. That's exactly it. And how do we know? Well, Y is in cost, so this means that's cost in dollars, and this is shirts. So I get $6.50 over 1, or $6.50 per shirt. All right, let's see if this is true. Now, if we were really thorough, we might pick every other sets of points. So we might pick like 50 to 100, 100 to 200, 20 to 100. Like we might check all over to make sure it is. Why don't we pick another 2 points and see? And I think this time, if you don't mind, I'm going to pick these 2 points.
I have a question.
Yeah.
If you just divide the cost by the
No.
shirts,
No, horrible idea.
well, wouldn't that work for that section, correct?
No.
Like there's 50 shirts and it costs $3.60, but just for that area, shouldn't it give you like per one shirt equals this much?
No. Here, let's do, no, I do. I'm trying to come up with a reason. I mean, me saying no isn't really that helpful. I get that. Let's see. Let's take these 2 points. Hold on. All right, Keith. No, I know. I got to figure out why I can say no. Let me do this next point, and I need to tell you why I want to say no, and I'm not doing that yet. So you've perplexed me. So well done. Every good student should perplex a teacher. Nice move. All right, let's do 685 minus 360 over 100 minus 50. So we get 325 over 50, and what is it? 6.5. Okay, what would happen if you did 360 divided by 50? What would you get?
I understand why you can't do that.
7.2. And what happens if you do, I can do 685 divided by 100, you get 6.85. Right? Neither of those is 650. So I've given you an example. I still haven't explained why. Let me come back to the explanation. Let me think about that. But do you see how, with a concrete thing, this example, it doesn't work?
Yeah.
All right. Elizabeth?
It is because the function for this problem is the average rate of change, not just the rate of change for one. If you said they sold 200 shirts and they made $1,335. How much per shirt? You could answer that question, but the question is the average rate of change from 20 to 200 shirts, because in one quarter they might have sold more shirts, and they might have charged more, and then in another they might have charged less.
I feel like it does. I feel like it has to do with the average rate of change as opposed to how much it costs for. So I guess this is the thing. In the question you're saying if we do 165 divided by 20, we're saying it costs this much per shirt if you order 20 shirts. And if we do 360 divided by 50, it costs that much per shirt if we order 50 shirts. But we're trying to find out what's the rate of increase. So we're not really looking at, we're trying to find the average cost per shirt. I gotta come back. But do you see it doesn't work?
Like, I see that it doesn't work, but the way that I think it doesn't work, like, makes me think that formula we're using actually doesn't work.
No, that's wrong. All right, so believe me, the formula we're using does work.
It's higher for like 50 shirts than it is for the average shirt. You know what I mean? Like,
hold on. Let's figure out. Let's put it into a formula and then see if we can get it to work. All right. So then maybe I can at least convince you what we're doing does work. So explain what the slope represents. Well, if I had to put, did someone say this? It's $6.50. Oh, we didn't really finish that. You said it, Evan, didn't you? I didn't write it though. $6.50 per shirt, right? I didn't say per shirt, right? Per shirt. Per shirt. What if I wanted to go the extra step and actually find the equation, the linear equation? How can I go about doing the linear equation? And how many people want to find B? How many people want to find the B? Yeah. If we don't have B, how many people want to use point slope? Everyone, put your hands up. Put your hands up. Watch how easy this is. If we just know the slope and a point, I can pick any point there, and I can say, okay, the equation's y minus 165 equals the slope, which is 650 times x minus 20. Do you see how all I needed was that point to plug in? And then I'm finished. I don't have to do any more, but let's do a little bit more. I'll just make it look nice for you. I need someone to do 6.5 times negative 20, and then do plus 165. What is it? 35? Okay. I think maybe, Keith, maybe. All right, so we know that it's $6.50 per shirt. In this equation, what if you ordered 0 shirts? It would cost $35 to order no shirts. That's crazy. What does that $35 represent? Could. Like shipping or...
One price, and you have to add $6.50 for every additional shirt.
Yeah, like just a startup, just to like talk to these people about printing shirts for you. Like once they set the printing process up to print shirts, that costs $35. Every other shirt costs $6.50 from that. So this is why I feel good. Your method didn't include the fact that there was this set fixed cost at the beginning. So do you feel better now that I might be right? All right, good. We should always remember that. If you're ever in doubt, I'm right. Okay. That was supposed to be a little bit funny. Thanks. Because I will be honest, there are many, many times this year where I'm going to be wrong, and it's important for you to tell me when I'm wrong. All right, thanks. That was a good conversation. It confused me a little bit.
You ever try to get people with that?
I'm waiting for that day.
Like, you guys Lotus sitting in that chair and just have that. You can sit out there with a chair and just write a message. Hi, Lotus. Whoa, what's happening?
I have not.
On Halloween, have them sit there and be like, hello.